Okay, good afternoon. Now, this video recording is a presentation of my final year research project on teaching intermediate electromagnetism course using computational tools. This project is done in two parts. The first part is the development of computational materials to help students in their learning of electromagnetism. The second part is a research into investigating the actual effectiveness of these computational materials towards student learning. Now, I want to take this moment to acknowledge my advisor, Dr. Koh, for his invaluable input throughout the timeline of this project. This will be the content for today's presentation. We will start off with the motivations for this topic, followed by an introduction to the computational materials we have developed. Then, we will proceed to the research segment, where we will talk about the aim, methodology, and results analysis of our investigation. We will also look at our students' survey responses regarding their attitude towards scientific computing. Finally, we will end this presentation with a conclusion. So what is our motivation for choosing this education topic? I would like to mention the importance of Maxwell's equations and the wide applications of vector calculus as a mathematical framework. Instead, I believe a short summary of the literature review in my report would be the best answer. So students encounter recurring difficulties in their learning of electromagnetism. Many face troubles understanding vector fields graphically. They struggle to apply their math knowledge to physical contexts, focusing too much on calculations instead of trying to understand the physical meaning behind their answers. It was found that some students still have trouble in graphical interpretations of divergence and curl, even after instruction. We know computational tools are commonly used by scientists and researchers looking to make sense of certain experimental data, or even when trying to understand the dynamics of an unfamiliar system. Can we perhaps flip this around and use computational tools to teach instead? Are we able to use computational tools to address the problems that students have been known to face when learning electromagnetism? So to find out the answers to this question, we develop our computational materials with the intent to help our students in their understanding of various concepts in electromagnetism. Topics range from simple dot and cross products to slightly more advanced vector operations. The materials also span numerical integration methods, symbolic computing, as well as partial differential equations such as Laplace equations. A lot of emphasis is placed on graphical interpretations of these topics through visual plots. In addition, with the increasing demand for computational skills in the 21st century, our materials, if anything, can help prepare our students in their future careers. Now, strangely, there seems to be little to no research literature on the use of scientific computing as a teaching medium. Therefore, research into the effectiveness of our computational materials for student learning in electromagnetism is actually an appropriate extension to this project. The aim of our research is to then investigate the effectiveness of using our computational materials in helping students develop their understanding in electromagnetism. We have limited the scope of our research to just vector operations due to the limitations in time frame of this project. Of course, we need to quantify this student's understanding, and we do that by defining 3 competencies a student should possess for vector operations. We have determined the first student competency to be structural understanding of the 3 basic vector operators. Anna Spart proposed an ontological structure towards how students interpret abstract mathematical concepts, namely a structural interpretation where math concepts are viewed as objects, or an operational interpretation where they are viewed as processes. One example given by Spart is the notion of a circle. It is possible to interpret the concept of circle operationally as a process. A circle is a curve obtained by rotating a compass around a fixed point. It can also be interpreted structurally as an object. A circle then, in this interpretation, will be the locus of all points equidistant from a given point. Now we see that structural understanding is conceptually more difficult to achieve than a context-driven operational understanding. Because these two interpretations are cognitive and not formal differences, it is hard for us to set clear definitions for what qualifies as structural interpretation versus what qualifies as operational interpretation. Hopefully, the examples given by Sfard in this table can convince you enough of the differences between the two. We determine our second student competency to be graphical interpretation of divergence and curl operators. Literature review tells us that students struggle to comprehend vector fields in graphical representations and have trouble determining non-zero divergence or curl in graphical plots of vector fields even after instruction. This could be because oftentimes traditional textbook-based lectures and tutorial classes place too much emphasis on problem solving and mathematical calculations without dedicating the same amount of attention to visual understanding of the vector operators. In addition, experts are of the opinion that graphical interpretation can help students in their understanding of these vector operators. Finally, we determine our last student competency to be conceptual understanding of Maxwell's equations. Since Maxwell's equations form the cornerstone of classical electromagnetism and are direct application of the mathematical concept of divergence and curl, it would be appropriate that students' ability to comprehend Maxwell's equations be included as a way to quantify their understanding of vector operations in electromagnetism. Because we have now defined the three competencies as quantifiers of student understanding in vector operations, we can measure their performance in each of the three competencies using diagnostic tests in order to determine their level of understanding. Comparing their performance then between the pre and post test will thus reveal any changes in their knowledge level. A diagnostic pretest was conducted for 74 students enrolled in PH 2102 Electromagnetism course in week 1 before the first lesson, since they had completed the mandatory multi-variable calculus course MH1803, which exposed them to vector fields and vector operations. We wanted to first establish their prior skills and understanding of these concepts. A randomly selected group of 15 students were invited to be in our intervention class, where they underwent two 1-hour computer laboratory lessons covering selected topics from our computational materials. These lessons are additional instructions, and they continue to attend normal lectures and tutorials together with students from the control group. Now, I want to make a note here that student involvement with the intervention class was completely voluntary, and selected candidates could withdraw from these additional lessons without consequences. Participation or non-participation in the optional intervention class offered no long-term advantages or disadvantages for the student. The computational materials were made available to all students after the post-test in week 4. 2 short scientific programming lessons were also conducted during the allocated lecture time in week 5 and 6 for all students enrolled in this intermediate electromagnetism course. So then, for the lessons, we selected the topics for the intervention class to directly target the 3 student competencies in vector operations, which we have identified previously. These lessons should primarily aim to improve students' structural understanding of gradient, divergence, and curl, while also giving equal attention to teaching graphical interpretation of these vector operations. Some examples of topics include basic introduction to dot and cross products as a warm-up, a mention of the various 3D coordinate systems, dedicated materials for vector fields and vector operations. There's also an introduction to symbolic computing, vector operations using symbolic computing, and lastly, related functions. Now, related functions, what we meant by related functions are the concepts of conservative vector field and scalar potential function. It is in our interest that by making a point for these functions, students can recognize and transfer this knowledge of conservative vector field over to a static electric field, for example, thereby making a connection for the electrostatic field to be defined by the gradient of some scalar potential function, and hence having zero curl. While this is not an attempt to target students' learning of Maxwell's equations explicitly, an appreciation for these related functions can translate to a better understanding of Maxwell's equations. Moving on to the post-test, the diagnostic post-test was then given to the student population in week 4 to determine the extent to which their knowledge of vector operations had changed. This was after lecture instruction up to chapter 2 of the course textbook, which covered the topic of electrostatics. Comparing between the performance of students in our intervention group with the performance of students in the control group, we can then determine the effectiveness of using computational materials as additional instruction aids in student learning of vector operations in electromagnetism. So moving on to a results analysis. Because we are comparing between which group of students have a larger improvement to their performance, we introduce two metrics that can help us analyze the gain in student understanding from the pre-test to the post-test. The first of the metric is normalized gain. Normalized gain is one common metric used in physics application research to measure student learning. It is determined by the ratio of the number of points gained between the pre and post-test to a maximum possible gain. Thus, a higher normalized gain rating will indicate a larger improvement or gain in knowledge. It is easy to see that this metric allows for a consistent analysis over diverse student population with widely varying initial knowledge states. The second metric is called effect size. Effect size is another common metric used in education research, but outside of physics. To quantify the gain in student knowledge, it normalizes average gain in overall score by the standard deviation in individual students' raw gain. Thus, a higher average size score will indicate a larger improvement or gain in student knowledge. By accounting for the variance in individual scores, this actually allows us to compare teaching effectiveness between classes of different sizes more fairly. This is relevant for a case of 15 students in the intervention class compared to 59 in the control group. Looking then at the normalized gain scores and the effect size score for our students, we see that the intervention group outperformed the control group, scoring a significantly higher rating for each metric, demonstrating that students in the intervention group had a larger improvement in performance and hence a larger gain in understanding than their peers in the control group. We now take a deeper look into the differences between the performance of students in the intervention group and control group by analyzing their answers for individual post-test questions. In the graphical interpretation question, students were given two vector fields as depicted in the figure and asked to determine if the divergence and curl were zero or non-zero. Our intervention group performed better than control group, with a higher percentage getting at least the divergence or curl correct, 80% and 87% for part A and B respectively by the intervention group, compared to only 58% and 64% for the control group. Now, a representative example of the kind of reasoning given by a student with the wrong answers is shown for the case of divergence in part A. This student made the claim that the divergence is zero in X but not in Y. This is an indication that students who got this question wrong still struggled with the concept of divergence as a scalar quantity. They either did not relate their understanding of divergence to flux or even had the wrong idea about flux. In the second question, students were given the vector field shown with the additional information that this is the field of an infinitely long charged cylinder. They were then again asked to determine if the divergence and curl were zero or non-zero. None of the students managed to get the correct answers for divergence, except one person in the intervention group. Students seemed especially unsure or were just uncomfortable with the use of Maxwell's equations. Specifically Gauss law, divergence is non-zero only where charges are present. In this case, divergence is non-zero within boundaries of the cylinder. A representative example of a wrong answer for this particular question will be an explanation that goes like, all arrows point inwards, so the divergence is non-zero, or any other arguments that divergence existed only along boundaries of the cylinder. This is an indication that students who got this question wrong had trouble combining information in text, graphs into a single coherent story. For the calculation of curl question, students were asked to calculate curl given the expressions of two vector fields shown, one in Cartesian and one in cylindrical coordinates. They were then asked to determine if the different field is a static electric field. Our intervention group again performed better than the control group, with a higher percentage correctly identifying zero curl as a property of static electric field, 60% and 53% for part A and B respectively by the intervention group, compared to only 41% and 31% for the control group. Without regards to whether students made the correct identification about the condition for a static electric field, almost all calculated curl correctly. So mathematical calculation is not a problem for many students, as expected given the heavy focus on calculations in traditional tutorial classes. In the last questions, students were asked to determine if the divergence and curl were zero or non-zero in three given physical situations. We see that with the exception of the divergence question in part C, our intervention class outperformed their peers in the control group for all other questions. This is indicative that a better understanding of divergence and curl in vector field aids students' conceptual knowledge of Maxwell's equations in differential form. Now, a survey was conducted for all students, assessing their attitude towards scientific computation. The average feedback was that students considered themselves to be fairly weak at scientific programming for electromagnetism, but are willing to use computational tools as a learning medium. They were also convinced about the important roles these computational tools would play in their study of electromagnetism. Our intervention group actually gave a fairly positive response in support of scientific programming, helping the understanding of the electromagnetism subject. We believe such an intimate feedback from the students themselves reaffirms the effectiveness of computational tools in student learning for electromagnetism. Before we conclude, some key takeaways we can draw from our result analysis are firstly, that traditional instruction focused too much on mathematics, wasting the opportunity for developing in students the understanding of fundamental physical concepts in electromagnetism. Students are thus fairly proficient with the required mathematical techniques, but struggled when they needed to make sense of the context of their calculations. Computational work can address this missed opportunity through a graphical instruction approach, specifically targeting students' qualitative understanding of vector operations in electromagnetism. We see that developing students' conceptual knowledge of divergence and curl in vector fields aids their understanding of Maxwell's equations in differential form. Thus, in conclusion, this brings us to a conclusion that the computational modeling-based coursework is in fact a viable and effective teaching tool to complement traditional textbook problem-solving based instructions for electromagnetism education. Our results reaffirm expert opinions that graphical representations are essential for student learning to conceptualize the abstract mathematical structures of vector calculus. This slide shows all the references that we have made in this presentation. Thank you.